Welcome to the University of Sydney. My name is Tim Bedding and I'm the head of the School of Physics here. I'm going to introduce the person who's going to introduce the speaker. So I'm going to introduce Professor Ben Eggleton. Many of you here already know him. Ben is a professor in the School of Physics. He is a laureate fellow of the Australian Research Council and he's also the director of the Centre of Excellence known as QDOS. So please, Ben.
So tonight we are going to hear from one of the world's leading optical physicists, Professor Federico Capasso, who is an absolute legend. And I'll say more about Federico, but let me tell you about the reason we're here, the Dr. Peter Domachuk Memorial Lecture, which was established after Peter sadly passed away just over 2 years ago at the age of 33. Peter was a young researcher in the School of Physics, a respected physicist who had been with the school for many years, a PhD student in the School of Physics. He had worked overseas at Tufts University, had returned back to Sydney where he was starting to establish his own research group, and as I said, very sadly passed away too young. And tonight we have the pleasure of hosting Peter's parents, Mr. and Mrs. Domachuk, who were in the audience. Peter's parents commemorated not only his memory but also his deep love for science by most generously establishing and committing in perpetuity to this series of lectures in his name. As I was explaining to Federico, this lecture series will go on forever. Thousands of years from now, there will still be, every 2 years, a lecture that will fly one of the world's leading physicists out to present a public lecture. So to Mr. and Mrs. Domachuk, on behalf of the School of Physics and the community, we thank you for your generosity. So the vision for this lecture is that it will offer on a biennial basis in perpetuity, as I said, an opportunity for the students, academics and researchers here at this university to hear a global leader in optics and experimental physics speak about their work and their field. Federico is actually going to be on campus for a few days. He'll be in the school tomorrow. He's talking to people. If you're interested, particularly the graduate students, please let me know and we will find a way for you to spend time with Federico tomorrow or on Thursday morning. The lecture will not only remember Peter, but acknowledge what he was doing. Peter was a young researcher, passionate about interdisciplinary science, working across boundaries, passionate about outreach and entrepreneurial, and I think those qualities can also characterise Federico Capasso. It's also worth mentioning that the lecture is administered by the Institute of Photonics and Optical Science at the University of Sydney, which is an umbrella organisation spanning across faculties and departments, and I want to acknowledge my colleagues on the IPOS executive who were involved in deciding who we would invite, and many of those people are in the audience. So I have the great pleasure in introducing to you tonight Professor Federico Capasso. So let me say a little bit about Federico. He is the Robert Wallace Professor of Applied Physics at Harvard University. His research cuts across several disciplines in basic physics, applied physics and engineering. We were discussing that we are both physicists and engineers, so we somehow have spanned across those disciplines, and we both worked at Bell Labs, which is where I first met Federico. His research spans, as I mentioned, optics, semiconductor physics, mesoscopic physics, solid-state electronics, optoelectronics, and micromechanics. He spent 27 years at Bell Labs, where he did research, became a Bell Labs Fellow, which is a big deal, and held several management positions, including Vice President for Physical Research, which is quite a title, Bell Labs being the preeminent physical sciences laboratory of its generation. That was the preeminent physics lab, and Federico was running that lab. I recall hearing Federico speak for the first time probably in '96 when I was a young postdoc and I had just arrived at Bell Labs, and Federico was on the stage at one of the photonics division meetings in New Jersey, and he was speaking very dynamically, passionately about the quantum cascade laser, this technology that had been pioneered by his group at Bell Labs and was an absolute game changer for applications of lasers, and it was the same energy that we're going to hear from him tonight, I'm sure. He was a legend then, 20 years ago, so he really is. It is a great honour to have him here today. I mentioned that he was talking on the quantum cascade laser. His group invented the quantum cascade laser. This is a semiconductor laser that emits in the mid-infrared portion of the electromagnetic spectrum. It's now widely available commercially, being used in applications such as environmental sensing of gases, pollutants and homeland security. He is a member of the National Academy of Sciences, the National Academy of Engineering, a Fellow of the American Institute Academy of Arts and Sciences. He's won numerous prizes, the King Faisal Prize, the Berthold Leibinger Prize, the Julius Springer Prize for Applied Physics, the APS Arthur Schawlow Prize and the IEEE Edison Medal. And for those of you who like metrics, he has published 500 journal papers at least, and an H number somewhere between 80 and 100, depending on which citation engine you use, but that puts him right up there in the absolute stratosphere. So it's a real great honour to have Federico in Sydney for a few days, and a great honour that he's speaking and presenting in the Dr. Peter Domachuk Memorial Lecture. So please join me in welcoming Professor Capasso to the stage.
Thank you very much, Ben. I like to think of myself as being a designer scientist. I like to design new materials, and recently my interest is actually turned to so-called kind of structured light. How can we design light in an interesting way and investigate the interaction between the structured light and materials? So I want to start with the Year of Light, which is an exciting thing. In fact, it was celebrated recently in Paris, the beginning. And it's just everywhere. See, light is a cross-cutting, optics is a cross-cutting discipline that connects different fields. In fact, what I tell a student, if you get into optics, you are able to get skills that will allow you to work in biology, medicine, atomic physics, and so forth. So it's very exciting. And last year, both the Nobel Prize in Physics and Chemistry were for optics-based technology, the one in physics for light-emitting diodes, the one in chemistry for super-resolution microscopy. So this is the celebration here. As the Secretary of the UN said, light sciences are a cross-cutting discipline in the 21st century, in the spirit of what I just mentioned before. So there are many key themes, but one theme that is going to come across often in my talk is light technology provides solution to global challenges. So in the last, I would say, it's fair to say, started from 20 years, we have seen a convergence of different disciplines. And one of the reasons for this convergence is nanotechnology and actual nanoscience. This was predicted actually in a famous public lecture given by Richard Feynman in 1956. What he said then, if we concentrate on a scale that is not quite the atomic scale, but the so-called mesoscopic scale, very exciting phenomena can happen, and that will bring together different disciplines. And he predicted, for example, the scanning tunneling microscope. The concept was there in his lecture and so forth. So essentially, we can say that at the nanometer scale is where the sciences converge. And these are some of the building blocks, you can think in terms of Lego. Biology, of course, it's a building block, which is DNA. In chemistry now we have carbon, not only buckyballs, carbon nanotubes, graphene sheet, and you just name it. In physics, it started a lot of exciting work on ultra-thin layers, nanometer scale, and down to nanocrystals and so forth. In optics, a very exciting topic is artificially structured optical materials that are structured over the length scale substantially less than the wavelength. So I will start to tell you a bit my story of research in nanoscience that started to look at a spectral region where it's very interesting and for application that is starting to explode sort of in the last 10 years. And it's a so-called mid-infrared spectrum where most of the molecules absorb light. So it goes roughly, you can say, between I have got this scale here has actually gotten mixed up. I'm very sorry. For some reason, this happens with PowerPoint. You know, never use PowerPoint too often, as I've probably done here. But the mid-IR goes roughly from 3 micron to sort of 30 micron wavelengths, and then we go into the far infrared. And the applications are wide range from security as to environmental monitor. I mention in particular because it's having a major impact in atmospheric chemistry. The industrial process control and pharma, for example, controlling the quality of medicines. It's an important application that is going to be developing a lot in future years. And the problem that the mid-IR hasn't had so far a lot of traction is because of a lack of a compact laser source that can be tunable in wavelengths over a wide range. So I'll tell you the story. Before the advent of the quantum cascade laser, this was the situation, basically. You see, there are a lot of great lasers in these regions here. The diode laser used for telecom capture the near infrared. Then there are visible lasers for many applications. But in here it was pretty sparse. The CO2 laser, carbon dioxide, is a pretty famous laser, but it's not widely tunable. It's fairly bulky and so forth. Quantum cascade laser are essentially using the same material system. You can cover an entire wavelength range from here to here by designing artificially these materials. Moreover, if you take one laser and you design it in a certain way, in of itself it is widely tunable. So I will show you that with a single laser like this, you can detect a large number of chemicals. So that's the reason of the impact. Sort of it came sort of at the right time through a combination of, we really don't understand how research happens, you know. After the fact, in hindsight, you can make up a nice story. But when you're in the middle of it, you really don't know. And often scientists themselves don't know what they're doing. They're playing around. I mean, the science in the audience know that. We just don't like to advertise it because it doesn't look good with actual funding agencies. but that's the reality. So I'm telling you a great story. I was at Bell Labs and I overlapped with a great scientist, Alcho, who is the inventor of molecular beam epitaxy. This is a technique that allows you to go, and it's commercially available now, essentially ultra-thin layers down to a few atoms, okay? And it's now, it's widely used. For example, this is ultimately how a quantum cascade laser looks like. It is an actual bar. This is the scale. It's sort of 10 micron wide. The length could be a few millimeters. It's made out of semiconductor. These semiconductors are layered. This is the active region here. So actually this shows the active region in particular where light is actually created. You see, it's kind of like a music, you know. You put in certain things, using the laws of quantum mechanics, we are designing the properties of these lasers. You can think of this as a new laser material, okay? And the thinnest layer here is about 8 angstrom thick, 7 or 8 angstrom thick. And the key point of this laser that by passing in an actual current, you apply a voltage between here and here, you get a current through, and essentially what you get, the emission of a laser photon per stage. As the electrons go from layer to layer, at each stage they emit a laser photon. So it's like a waterfall. It is an electronic waterfall that gives rise to a photon waterfall. And so it's not by coincidence that I put this here. Okay, so we use these ultra-thin layers, are called quantum wells, and you can design the energy levels. It's a bit like an artificial atom, but in one dimension. And what you apply then a voltage, and so what happens that the electrons are injected in one stage, they emit a photon, they get into the next stage, and so forth. And it's you can consider it again a new class of laser material designed bottom-up using the laws of quantum mechanics. This was our first paper. It took a long time to get here. It would be very difficult to do this kind of work now in an environment where we have to write lots of proposals and so forth. So I was kind of lucky to be at Bell Labs. And this shows one particular design for a quantum cascade laser that is designed to emit at 7.5 micron. This is a so-called energy diagram. Is the energy of the electrons as a function of distance. As I move down here, I apply an actual voltage. So the voltage drop from here to here is just this energy difference here. And they are based, the material is important but not so important. As long as it has certain characteristics, the key point is that these energy wells have to be fairly deep, okay? So that you can design, by changing the layer thickness, you can change this energy distance between the two energy levels that are the two energy levels of the laser transition, right? So it's tailorable. You can tailor it, for example, in this material system, all the way from around 3 micron to beyond 30 micron. In fact, you can go as far as 100 micron and so forth into the so-called far infrared region. Science is about people. Now, you might ask here, what the hell is Mr. Bill Clinton doing? What does he have to do with quantum cascade laser? Well, nothing directly, except this is my great collaborator, Al Shaw, when he won the Medal of Science, which is one of the highest honor in science in the US. And so he went to Washington with his mother and his sister to get National Medal of Science for the invention of MB from Bill Clinton himself. This was my then young group at Bell Labs. Have all become very established in their field. Jérôme is a professor at ETH, Claire is a professor at Princeton, and so forth. Now, once you have such a laser, we were immediately told when we got the first paper is, look, you can target lots of applications. This is, and particularly the group of Rice University led by Robert Curl, who is a Nobel Prize winning chemistry for the co-discovery of the buckyball, and Professor Frank Tittel really started to target systematically these applications through quantum cascade, with quantum cascade laser. Most of them, many of them. I want to focus on two stories. One is a nice one because it says about how we can impact with optics global challenges. And this is the story of atmospheric chemistry. And I'm also going to say something about the medical diagnostics, because I believe these lasers have a big future for breath analysis, so that you can detect early disease, very early. So, well, we know that the population drives, the increased population drives the consumption of energy, which is estimated at 40, well, you can be off here by 20%, whatever, 40 terawatts of power. This dramatic increase in energy means we are consuming more fossil fuels, and this produces a greenhouse effect which increases the temperature and global warming. This is no more a matter of debate. It is a fact. So now let me show you some dramatic pictures. This is the volume of ice, of Arctic ice, as a function of actual time. Look at the dramatic decrease in the coverage of ice. Essentially from 75 here, 77 to now, we are down by essentially a very large factor, right? Just look at here. And this is going to continue. The prediction is within the next 5 years. In September, there's going to be, which is that the period of the minimum ice sheet area, we will have just water. There'll be no ice anymore, with some uncertainties, of course. So this is one of the effects. So now I'm going to tell you what QCLs can do in terms of sensing. This is very simple. Molecules have these vibrational modes. They will absorb infrared light For example, this is the spectrum of nitric oxide here. And in the typical geometry, what you want, you have a multipass cavity. You see, we want to measure concentration down to parts per billion in volume, in certain cases down to part per trillion. So what we need is to have we have to increase the sensitivity, and so there are these multipass cavities which can go from a few meters up to 30 meters, 200 meters, and so forth. And then there is a detector here. So I want to show you a beautiful study that my colleague Steve Wofsy, who is a world leader in atmospheric chemistry, did at Harvard using quantum cascade lasers. He flies these high altitude plane, and essentially the so-called HIPPO mission the plane starts from the South Pole to the North Pole here, and as it goes up the actual latitude, it changes altitude, so it samples both the troposphere and the actual stratosphere and detects essentially with high precision the concentration of the greenhouse gases and other gases as well. So this is an example, and why is it important? In order to be able to predict, to have predictable climate models and so forth, the distribution of these chemicals in actual space is very important. And these are, see the measurements of this precision, this is the concentration. They were able to measure profiles of CO2, typically levels of 100 parts per million with a precision of 30 parts per billion. So the precision is actually very important. And this was a mission that lasted actually 3 to 4 years. This shows a typical data, what the plane does. You see it goes from the south to the north. This is the actual trace of the plane. These dotted lines here, so it goes from the troposphere to the stratosphere, in this case measuring carbon monoxide, in this case carbon dioxide. This color code is the actual concentration. And why are these measurements important? Because they resolve the vertical and horizontal structure of the atmosphere, of these gases, many other also methane and N2O and so forth. And the first to provide a high resolution section of the atmosphere for these gases. And the key point that these patterns provide new information about the location of the strength and the emission of greenhouse gases to the atmosphere. So that's kind. Another great collaborator of mine is Professor Jim Anderson. He's famous for many things in the field. One was he was of the people that contribute to write the Montreal Protocol for to reduce the actual ozone hole. Okay. So years ago, when we invented the QCL, he jumped in it, and now he's flying them both with actual drones. This is a drone. Drones are not only bad things, they also do some good things. This is a good thing that they do. Drone for the detection of chemicals in pervious region. But I want to share with you some recent data that he took. He also flies, not himself, but he hires these pilots. Many are actually former war pilots. This is a plane that can fly as close as 5 meters to the actual ground. You can imagine how challenging that is, okay? And particularly, he's interested in measuring the emission of methane from the permafrost, from the tundra. Why is that important? Because methane is the most powerful greenhouse gas. It has about 20 times more powerful than carbon dioxide. So the worry is that as the soil warms up, there's going to be more emission of methane, and at some point is there a threshold beyond which you can get a huge release, basically. And it's a wonderful plane here. This is an antenna that has a GPS, but also can measure actually the speed of air with respect to the actual plane. It has different so-called axes. It can measure methane, it can measure carbon dioxide, it can measure also the isotope of methane, like with carbon-13 and so forth. And these are some of the data. taken in this flight over Alaska, okay, where they measure the actual concentration of methane as a function of height from the actual soil. And it's quite significant that there are signs of buildup depending on the actual season of the emission of methane. So there are some concern. The key thing is not to make catastrophic type of prediction, but to inject as much science in as possible, so that decision hopefully can be made not just based on emotions and so forth. Now, this is another fascinating story. This has just appeared in Science. You all know about the Curiosity on Mars, that wonderful PR it got, wonderful science. In the last report on Science, the Curiosity used a cascade laser to detect methane on Mars with a mean value of less 1 part per billion in volume. So it's a good story, that atmospheric chemistry. I would say there would have been zero chance that I could have predicted after the invention of this laser that this would be a leading type of application. If anything, I would say something maybe completely different. Breath analysis is very interesting. These shows work done by the Rice Group in collaboration with Johns Hopkins, measuring essentially, the key idea is this. Okay, you breathe, you go as an outpatient into a hospital, you breathe into an actual chamber, and a laser tunes in a particular chemical, and so this should lead to non-invasive, real-time, highly selective detection of certain pathogenic condition. So there is a potential quite large impact. In the US in particular, it must be moderated by the long approval by the FDA of tests, new medicines and so forth, which could take 5-7 years, even though things are on a fast track, but it looks quite promising as a technique for medical diagnostic. I started a company at Harvard which makes this product. It's called EOS Photonics, with the postdocs, my postdocs, and postdocs of Professor Jim Anderson, and we make the Matchbox. It's actually a compact array of quantum cascade laser. The idea is this is an array here, okay, you can show it, and there is a microcontroller, off-the-shelf microcontroller that fire pulses, so it can light up at different time, different lasers. So the laser can span a wavelength range, typically more than an actual 1 micron wavelength, so you can target simultaneously, practically in real time, all kinds of different chemicals. And this is the key point, and we are working on insertion into full systems. Very quickly, some data here. In fact, this is an array of 32 lasers. Here they are filed in actual sequence, and you can see the spectrum. This is the mode. You can cover essentially from 8 to 9 micron. So we think, our goal is to make compact, small sensor that can be carried anywhere. These work at room temperature, these lasers. They have to otherwise, or they can be T-cooled, of course. And so there is a huge interest, actually, to embed sensors everywhere within the actual network. And so you have heard about the Internet of Things. At the beginning, I was actually skeptical, but when I looked into it, so I think this is really something. I believe that mid-IR photonics, okay, based on QCL, is poised to have a major impact in these areas. Network sensor. And basically, because I can see the price is going down. You can now buy them for down to $500 pulse per unit. You know, it all started with telecom laser. They would cost $15,000 per laser. So people then said in the 70s, I remember at Bell Labs, this will never work. People that say that things will never listen to them, to the young people. Just do the opposite. That's the best recipe I can say. Okay, so I think there is a real potential of it. And so the goal is to small footprint, portable, high brightness, the devices that are exciting application of coupling these lasers to fibers and so forth. And in fact, if you look at the various studies about the technology roadmap from the Internet of Things, you know, over actual time, you can see that starting with RFID tags in supermarkets and so forth, surveillance, healthcare, transport, I think this is in full swing now, to other type of application, teleoperation and telepresence, the ability to monitor and control distant objects, like with every new technology, there is both sides. You can use it well, you can use it bad, that's a human choice. So just to tell you that the mid-IR is starting to explode, you can now buy this, this attachment to your iPhone, which is an infrared camera for imaging. Now, you know, the iPhone, I think, costs $300. This, the fact that an accessories cost $300, I might say, well, this is too much. But, you know, if there is a need, eventually prices are brought down and it becomes a pervasive technology. So, yes, I am more than optimistic that the mid-IR will really strike big because the time has actually come, because of the laser technology that is available, the detector technology. Also, now I want to switch gears and tell you how I got into this field here, which is that of designer light, I call. I'm going to start to review how an antenna works. Now, this antenna is antenna of Sputnik, old Sputnik TV. It's a V antenna, and that inspired us to do some new work. The key point of the antenna, it does a so-called impedance transformation, but that's a technical point I really don't want to go into, is to say, even though these are big radio waves, right, they might be meter long and so forth, what the antenna does, it concentrates it to a region much less than the actual wavelengths, right? We know that, right? It concentrates on an actual tiny chip inside your actual cell phone, on a very small dimension in your cell phone. So in the last 10 years, there's been a lot of work on making antennas for visible light, not for radio frequency. And the principle is very simple. You have light that jiggles back and forth. So what happens, charges oscillate. And as a result of this charging oscillate here, you have minus sign that says plus sign at a given time. You have a hot spot where you get a lot of concentration of field, of electromagnetic field. This is a resonant type of effect. As you scale this length, you can get resonances at different wavelengths. The key point for what we want to do is that nanoantennas can store light for different amount of time depending on the actual size. If I want to use a more technical terms, I would say that as light is incident on an antenna, it actually scatters it for what we want to do with a phase shift, okay? And what we have explored is how we can impart new optical properties to surfaces. So this is the era of so-called metasurfaces. So I'm going to start. So we have honestly, we started to say, let's revisit the old laws of light, of reflection and refraction. Refraction, we all know what it is, right? If we look at a stick that is immersed in water, it looks bent because essentially the light from here gets refracted, so there is a change in this angle here, so the object actually looks as if it's actually here. Now this was studied first by Snell in 16th century, and he came up with this law that I'm not going to actually put down. Who explains it beautifully? It was Fermat, the same Fermat of the Fermat's theorem in actual math. What he said is you can explain this thing that light follows the path of minimum time, the light beam. So the ratio of these angles basically is related to the ratio of speed of light in these two media. Typically, if you are in a more dense media, the so-called phase velocity, let me talk just about the speed of light, is actually less. Now, I want to tell you that Richard Feynman, his lecture in physics, had a beautiful analogy for this. And like Richard Feynman was a genius, he was able to explain most of physics in very simple things. So I got this from him. So you have a lifeguard now, okay, who is trying to save this gentleman here, right? Now, the lifeguard dilemma is, what is the best route to reach the actual drowning man? It's obvious that the straight path is not the best strategy, because the lifeguard can run fast here on ground, but typically swims slow, much slower than she or he can run. So this is not the best path. So what is the best path? The best path is to maximize the actual path. It's a compromise. So where she can go at high speed, you can cover this in actual lesser time because you go fast, and you are trying to minimize the slow path here. Okay, so what is this? This is simple, the law of refraction. It's the same math as optics. If you assume that the speed in actual land is whatever it is, and in C is this number here, by minimize this actual time, you come up with an actual law that is identical to the law of the way beams bent as they go from one medium to another. So I think this is quite interesting. So we have been asking now the following question. What if now we have a different, what if instead of having a simple going from shore to water, instead of a flat area, you have a cliff? Then you see the first thing you start to think, this is the most difficult path, because running here it's easy. Swimming is comparatively easy. Coming down this is going to take the longest time, right? So let me schematize this. Let's have a cliff of varying height here, whatever, and this is the limiting factor in terms of actual time. This is where whoever is doing the saving is actually going to go slower, just easily coming down. Now you could say but the person can actually jump. Consider this is so high that if he or she jumps, will actually kill himself or herself. So either using a parachute or jumping down, that's not allowed, which is a realistic assumption. So now you see that the path, what is the optimum path? The path is actually something, again, a compromise, but where you try to minimize this time here. And what you see, depending on the design of this cliff, you can have an interesting situation of this re-entrant path here. Now we can translate this. What does it mean for light? For light, it means a strange kind of refraction, negative refraction. So we have asked ourselves the question, what is the analog of the steep cliff of varying height for a natural light beam? Can we design the interface between the two media to bend light in arbitrary ways? And so you see, what we need to actually design is an interface which can delay light by a different amount of time at each point. This different delay is the equivalent of the varying cliff height. So that then I can hope to get negative refraction. Let me tell you, this negative refraction for the experts is different than mechanism that what you have for metamaterials. Okay, the physical mechanism is just different. So how do you create a tilted beam? Well, we have created a tilted beam essentially by decorating the interface of two media with different antennas. I tried to explain before that an antenna is an object that can delay the emission of light in different ways. So by changing the design, you have a delay in the emission of light that is different antenna by antenna. So these are the wavelets that are emitted by these antennas. They are spaced at a distance significantly less than the wavelength, so you can call this a metasurface, an effective surface, right? So then you can see, because these antennas will shift light in a different way, will phase shift it or time shift it if you wish, that light that is incident straight will be bent at a certain angle, and you can design the angle in any way you want. So this allowed us to generalize the laws of refraction to a metasurface. We use again Fermat's principle to minimize the actual time of propagation, and you find a generalized law. And this is the metasurface that we design. It would be too hard to explain exactly how it was done, but it's a repeat unit many times. This is gold on silica, and essentially what this different design changes the phase shift of light as we cross, as a point by actual point. So if when we come in, let's say at a certain, we can actually, we have this anomalous refraction. You see the beam, instead of going this way, goes this way, and you can design it also have an anomalous reflection. So this is designed for the mid-infrared, so we use quantum cascade lasers to actually test it, and these are some of the data that I want to show you. When you come in normal incidence, you see that light is reflected at a certain angle. Here we can vary the period, this unit period. As we change it, we can deflect more. And so this is kind of an interesting demonstration of what you can do with artificial surfaces, with artificially structured surfaces. Now at some point, with one of my postdocs, we asked the question, well, do we understand why lenses are thick? Of course, you can look it up in any actual textbook. Okay, but let me explain it in terms of actually Fermat. Okay, in order to focus all the actual light rays, okay, in the actual same point, essentially all these times of propagation for the different beams have to be the same. Now light travels faster into free space than in here, and so if you make a spherical surface like here, based on just what I said, what you can see, that you can arrange the light path to have the same delay. But it's actually blurred. You get some aberrations here, spherical aberrations. So what we designed, this is my postdoc Francesco Aieta and another postdoc, this flat lens here, which is optically thin. We asked ourselves, can you make a lens that is not spherical, that is completely flat? And what you can do it by using these antennas, the same antennas that are shown here, but with a radial type of disposition here, okay, what you can actually, of course, the time to propagate from here to here varies point by point, right? So how can you focalize everything in here? Well, what you do is you have to add the time delay, which is induced by this antenna here. So at the end of what you have done is to actually be able to converge in a single point. This lens was actually made quite a splash, but it worked only at one wavelength, so we have been working hard to make it multi-wavelengths, and I'm saying here, this is interesting, this is not a lens, so it is a lens. It's actually coffee mug, but it looks kind of like a lens, okay? If you see that Zeiss makes this lens called a super achromat that corrects for chromatic aberration so that all colors are focused in the same point. This can be done also with our flat technology, and it's shown here, which is just a science paper that we published. You see, if you use spherical lenses, the only way to correct for multiple wavelengths and to add other lenses. This is commercially available, so is this, and so forth. By a design that is a bit too complicated to explain here, this is now we got away from metals because they are lossy. This is simply silicon on silicon dioxide. By patterning in a certain way, we have shown that you can actually correct for this chromatic aberration and converge different colors in the same focal point. These are the actual data and the simulation, the bottom, the simulation, and the experiment. So it's quite interesting. The last topic, I know there are how many more minutes? Okay. So this is So you see, you can engineer what we call this is flat optics. And I will give you some technology things because when we look on new technology, I tell my students we have to talk to companies. We can't just be sitting ourselves in a university lab as academics dreaming up new things, then who knows whether it's useful or not. It's actually more likely in many cases that it's useless. So we got to ask this question. I'm going to get back later to this. We have been very interested in optical vortices. This is an example of structural light. These have been known for quite a long time. These are beams, essentially, where the flow of energy goes in a spiral around a certain direction here. So the direction of energy flow is actually different from the propagation direction. It follows a path like this. And believe it or not, like often happens for fundamental thing, eventually find some application. Now there is an interest now on these vortices to encode the optical information. The key thing is these vortices have an intensity pattern that has a zero of intensity at the center. And actually this light carries not only spin angular momentum, we are taught often, and it is a mistake, that photons have just spin angular momentum. That's actually incorrect. If you prepare them in such a state of light, photons can have an orbital angular momentum. And this has been shown down to the single photon. So this is a quantum mechanical angular momentum, and it's kind of fascinating. So we have asked ourselves, we create one of these metasurfaces? So if you design them in a way, you see, that you have a rotational symmetry here, this is not a lens, you actually can create a vortex. These are our data. But this, you see, shows that you have an intensity minimum. How can I show that it's a spiral? Okay, that's the key point. The physicists like to say, how do I get the phase information? So you do simply an interferometric type of experiment. You create your vortex beam by shining light with a quantum cascade laser on this surface here, and you create your vortex state, and then you do an interference with the original beam. And the interference pattern shows a spiral. Now you would say, you need math to explain it? No. Actually, in most cases, you actually don't need math. Of course, you need to be quantitative at the end, so you don't want to send the wrong message. But most of the time, there is a simple explanation for things. So I can look at the interference now that I have sort of quasi-spherical wavefront from the actual laser, or it could be a plane wave, it doesn't matter. I interfere it with this corkscrew light doing this. What do I get from the interference? I get an actual spiral. And this shows our data confirming actually that it is a spiral. I want to give you, so those of you that know about diffractive optics might ask, what's the connection and so forth. So, when we made the first flat lens, I was called by the person in charge of Google, Google Glass. For those who are graduating soon in optics, let me tell you, Google is the most exciting place to do optics. I'm serious, so look into Google. It's not easy to get hired. Anyway, and so I talked there to Bernard Kress, who is, his title is Principal Optical Architect at Google, and I asked him, well, the first thing they told me, Federico, can you make a cell phone as thin as a credit card? Then I understood, one of the limiting factors of this cell phone is the actual thickness of the lens. But when I talked more to them is this, these metasurfaces allow you a big technology simplification. With a single digital pattern, one mask level for the experts, you can create an analog profile of phase. So you can do basically things with a single mask. Moreover, it's much more simpler to do broadband. One of the problems of diffractive optics is to do, in a simple way, broadband or multiple wavelengths. So I think it's a quite interesting approach. So my vision is that flat optics will have a future. I'm saying that because we are talking to companies. We kind of see it coming to do well-established components in this more compressed way, small footprint compact. The holy grail is to make a high-speed spatial light modulator. A spatial light modulator you can buy for Hamamatsu is a box of a certain size. You send in light, you can create any kind of light. It uses either liquid crystal or MEMS, so it's slow. We are talking of speeds at most, maybe 100 microseconds and so forth. Can we make this device 1,000 times faster? We believe actually there is a way using flat optics and using some modulation scheme to go down to nanosecond. And so these are the applications. Our aim is to demonstrate these flat optics on stretchable materials, rollover displays, all kinds of things, pattern the facet of fiber. There are major opportunities in the mid-infrared when you have poor refractory materials and so forth. So I think it is wide open. And I need to thank the collaborator for this part. Zhao Lin is actually University of Melbourne, now very talented. If I didn't have good students and good postdocs, I would be just writing proposals basically and just waiting for things to happen. But fortunately, they're energetic people willing to take these challenges. So I want to conclude again, this is exciting because it's the year of light. Light technologies provide solution to global challenges. I gave you just a glimpse. There is much more to it. And so with this, I have concluded, and thank you for your attention.